So I'm Deepak, and this talk is going to be about how can we learn to discover um, learning algorithms, essentially. So learning to learn. About me, I'm a PhD student at University of Santa Barbara. It's UCSB. I'm supervised by William Wang and Professor Eric Wang. My topics include I generally work on automated discovery, but I've also been interested in proactive agents. I am really interested in how to go from reactive agents where we are giving agents the task, and then they do tasks autonomously, going from there to agents observing our user actions, our notifications, and giving us tasks. Okay, is it okay if I do this? So these are the two topics I'm interested in. Past publications, in the first year, I worked on multi-aspect feedback. Back then, it was a very big thing where LLMs were able to self-refine their own ideas, and we found that okay, if you divide the feedback loop into multiple things, you can have better performance. Then I worked on MLGym, which is basically a precursor of auto research, where you have an agent continuously making changes, optimizations in the ML research environment, and it is connected with the Docker environment essentially, and can just do anything. Right? It's secure, but back then the models were not that good, and the main issue with MLGym and all the frameworks back then was okay, how do you stop these language models from reward hacking? Because it is very easy for them to just give up and then just reward hack, right? And also how to scale up the number of tasks we have in ML. So then we started working on DiscoGen, which essentially is, I'll present a small background. I'll try to be quick. And this whole idea of DiscoGen is based on meta-learning research, which has existed for decades now, and we wanted to try it in the age of research. I'll try to explain what DiscoGen is, and then also try to give some ideas of okay, what's next for DiscoGen, and also what's next in terms of research ideas. How can you use this framework? Okay, so in meta-learning, you have this agent and environment setup where agent is taking actions in the environment and getting rewards, states, etc. But at the same time, you have another loop, which is actually trying to learn the agent itself. So you can think of an agent as a neural network, but how to structure that neural network, what is the loss function, what is the optimizer, all of this is learned by the meta-learner. And then you can take this meta-learner and you can apply this to a different problem, and it can create an agent for you. Right? Here's one example where the agent is trying to write the optimizer loop, the optimizer function, and once the agent is trained on this particular environment, it gets the final return. It goes back to meta-learner. It will update a new optimizer, and it will try it again. And it goes and goes in the loop. And finally, what you get is very optimized optimizer code. You can think of maybe it will discover muon. It doesn't, but maybe it can. Maybe it can discover the next muon. Alex Goldie was the lead on DiscoGen project, and he has worked on this before as well. How can we make learned optimization better for reinforcement learning? There are three main problems with RL. One, as you keep training your RL models, you have a plasticity loss. What that means essentially is, as you keep training it, the model's ability to absorb new knowledge keeps going lower, which is not a good thing, because you want a research scientist, you want like AI research scientist to keep absorbing new knowledge. Second is exploration. I think last in Elliot's talk, someone asked a question, how do you balance between exploration and exploitation? That's an age-old problem in RL, and we have still not solved it in some sense, not in a general way. And also, a lot of RL environments are non-stationary. Because of the agent actions, the environment itself is changing. And this is particularly true for ML research. As Elliot also mentioned, that the kernels can change, the GPUs can change, and all of that affects the training performance. So here's one cool old demo of a spider trying to walk. And this is what meta-learning essentially does, right? You try out different optimizers, you get all of them, right? You evolve in the optimizer, and you can learn the meta-learner. You can solve these problems generally by creating more and more and more environments. So by procedurally generating new environments, right? And if you optimize on a large set of environments, then it generalizes quite well. But these are again environments which are like maze or a walking environment where the spider is trying to walk, or like humanoid is trying to learn to walk. How can we apply this to machine learning? Right? I'll skip over this part a little bit. Okay, so one important thing is there are meta-learned algorithms, which is like LPG, LPO, which are basically a specific algorithm that you can apply anywhere else, which were meta-learned by some agent or by some meta-learner. And then there are meta-learning algorithms. The one that we focus on is auto research, which is basically LLM prompting. That is a meta-learning algorithm in itself. Then evolutionary strategies is another meta-learning algorithm, and the output is again one specific piece of code that you can run on any problem. The question is how far can we take these meta-learning algorithms? Can we make this into a whole research loop? And I have a very different definition of research. So I would like to draw a parallel here. So in auto research or any of these evolution frameworks, when we are solving, let's say, a bin packing problem or a traveling salesman problem, what we are essentially doing is we are benchmarking. We have one benchmark that we want to get 100% accuracy on, and we just want to continuously, and agent has full access to it, by the way. So we are doing benchmarking, which is very useful in certain scenarios. If you want a very specific model, yes, benchmarking is the only thing you need. But if you want to make generalized discoveries, that's not the way to go. You need to be able to check the generated algorithm on completely held out sets. And that's one of the main points of DiscoGen paper. This is the paper which I'm going to be talking about. It's how do you procedurally generate algorithm discovery tasks for machine learning? Because in machine learning, it's slightly easier to test the generalization part. There are many existing benchmarks for this. We started with MLagent Bench, Ayers Bench, RE Bench, MLGym Bench. So MLGym Bench is actually one of my previous works where we did the agent, Auto Bench, or LLM. Yeah, as you can see, there are like a bunch of these benchmarks, but these are benchmarks. You cannot use these for training a new agent. Or even if you do use them, even if you somehow able to create held out sets, they will still try to reward hack. The first problem is how can we learn from these? Because it's not scalable. These benchmarks typically have around 75 to 100 problems, and some of them have 10, 20. They don't have meta-train, meta-test splits, so you cannot test contamination, and also you cannot test generalization. And you also cannot make these tasks harder or easier on a given, right? And then also the diversity is limited because a human is writing this by hand, so you cannot really ask a human to just write a solution to every ML research problem in existence. We like to think that DiscoGen is one of the solutions. You create a procedural task generator and framework. You can select a bunch of domains, algorithm components. So each ML algorithm will have something like a loss, optimizer, training network, the network architecture itself. These are all algorithm components. Meta-train datasets, and then meta-test datasets. And then backends is something like, so for example, in different domains, you can have different backends that work. So for example, in LLM domain, in language modeling domain itself, either you can have a transform backend or you can have a diffusion backend. So that's what we mean by backend here. And then also evaluation type. So we don't only care about performance, we also care about energy efficiency, that amount of time it takes to train the model. Right? These are all also very important axes. So you also need to be able to do evaluation type. We have enough tasks that you can actually use these to train these models. And also since we have a separate meta-test data sets, it's very harder to contaminate. And another important thing is a lot of benchmarks that I've seen now is they take individual papers. So for example, papers bench is a paper from OpenAI. They took individual papers and they kind of crowdsourced the ideas from that paper, and they're trying to make the LLM learn from that or solve that problems. We go the other way. We are based on fields instead of one specific paper. So for example, on policy RL is a whole field. So can you generate an optimizer that works around the on policy RL domain or like off policy RL domain? This is how a normal config in DiscoGen looks like. So you define the task domain, it should be supported. You define the meta train sets. So as you can see, breakout and freeway, they are both environments in Minitar. So the agent will optimize its code on these two environments, but then when it comes to testing, the code will be actually tested on asterisks and space invaders. It basically checks if your agent, the algorithm that the agent wrote, is actually generalizing to other tasks or not in the same domain. And backend can be recurrent or a normal actor critic, anything. And another important thing is you can actually restrict the agents to only change the loss function. This way you will get a new loss function. You can also restrict the agent to only change the optimizer. So you can do mix and match of these different config styles. And the task basically has files. It is just a workspace that we give the agent. This is not an agent, this is just a task generator. So in theory, you can use Claude Code, you can use Open Code, any of the agents that are out there that work on files, and it will work. And then we have discovered files, which the agent wrote, and we have the split. So these are the task domains we have right now. And for each domain, we list the number of tasks that you can generate using that. So you can see there are actually greater than 1 billion tasks that are possible through this task generator. And this is very important again, because if you want to learn, you need a bunch of tasks, and they are different, and they should be different. This is an example of, so this is how auto research looks like. You have an agent which is writing code, getting some feedback, and then optimizing the code, right? This is the auto research part. Then the discussion comes in. You can continuously sample new tasks, and you can, once the agent has optimized on these meta train sets, you can actually evaluate it on a meta test set. ADA here just means algorithm discovery agent. The most important question is, okay, you can generate 1 billion tasks, but are they actually different from each other? So we did some analysis on that. So we did some rank correlation of different LM models on different tasks. So you can see, so for example, base optimization is the domain, and then you are only changing the optimizer. So you can have multiple tasks from a single domain, and you can see there are a lot of correlated tasks, but then there are also a lot of uncorrelated tasks, right? And same with, like, this is meta train, and this is the meta test. You can see in meta test, actually, the correlation is very low, generally, between these tasks. So you can actually test it properly. Due to budget limitation, we were only able to check 3 models: GPT-OSS, DevStrel, and DeepSeek 3.2. I think OpenAI, like ChatGPT or Claude Code, may do much better than this. But as you can see, for a lot of these tasks, the meta test scores actually look worse. So this is the ELO score. In ELO score, comparatively, it is doing better than the baseline in meta test. But if you actually if you go to the paper and you look at the task success rate in meta test, the agents do very well on meta train because they are optimized on that, but not very well on meta test. So they are not writing generalized algorithms. Again, the big question is, how can you use this? Can you use SysQL to learn to discover? Right now, you can do prompt optimization. So you can have another loop on top of it where you have an agent which is optimizing. By the same time, once the optimization is complete, then the loop can change the prompt. And then again, you can run the same loop, right? So right now you can do prompt optimization, and we did this experiment in the paper. So you can see, as you also increase the number of tasks, the success rate goes up. So this is the evidence that generating more tasks or letting the agent optimize its code on multiple tasks actually helps the agent in writing better generalizable code. Right? What else is coming? Well, we have more tasks planned. So we want to include protein docking, self-driving, diffusion. We actually already integrated diffusion models in the framework. We also want to have like a private discussion task API so that no one else can fit on them, and we can keep that as a pristine set for evaluation. Open source contributions are welcome. If you have any interesting domains, like I feel like protein docking is a very interesting domain in this. If you have any interesting domains, please let me know, or please feel free to contribute. Or if you have any idea for new evaluation, more modules for existing and as well as for new domains, that would be interesting. We also want to create a leaderboard. But more than that, what this enables is you can keep going one level up. So you can keep going one level meta again and again and again and again, right? Which I think is very interesting, and it kind of enables the self-improvement loop in a generalizable fashion. And again, can we discover a better discovery agent itself, right? So that's again a one level meta. Some ideas on that is, can we just do simple RL? I think generally RL works very well, but you will again hit the problem of exploration versus exploitation, which will not be pretty. So we started with prompt optimizations. You can always do that, and actually it works pretty well. Can you also automate the agent scaffold design itself, right? And how can we do this without blowing our budget? That's where like the test time training maybe comes in. And if you can make test time training work generalizably, that would be very interesting. And again, most frameworks focus on discovering the best algorithms. I think that's one part of the equation, but you also need to discover most efficient algorithms, most quick algorithms, right, and low memory algorithms. And short is sort of like code golf. I'm not sure how many people are familiar with a thing called code golf. So how small of a code can you write to do the same thing? Right? I think all of these X's are very important, and it's in their own way. And Discord right now supports all of these evaluations for all of the domains and all of the training and testing tasks. Right? And then the last question is like, are there any interesting inductive biases to inject into the agent? Which is again very interesting problem and a research problem in itself. And we are just claiming that Discord actually enables all of this. This is again one of the big ideas. Can you create an algorithm world model where the model itself, without running the code, can predict what is going to happen? Right? You can generate a lot of data. Can you train to predict a performance for algorithm data set? That would be very interesting. So you don't need to actually run the model, which solves your TTT problem. Right? So you don't need to train at test time now. Now you have a world model which accurately predicts the performance, and that improves the training loop. And thank you for that. There's a GitHub link over there. Feel free to contribute. And this is Alex, by the way. He's the project lead on the paper, and this is me. It was great talking here. Let me know if you have any questions.
So for the part that you mentioned that it's not sufficient enough to just discover the best algorithm, but also we need to consider the cost and other metrics as well.
Mm-hmm.
Has Discogen started to work on something on this, or is it just a proposal for future direction?
So the evaluation for all of these X's is already in there. So we already have the evaluation for like, okay, is this the most efficient algorithm or not? Right? We don't have experiments on that because of API money and GPU cost, but we do support the evaluation of this.
So I have a proposal. Maybe we can have like multi-step or multi-phase optimization. Like let's say that you have a couple metrics, and you first optimize for the metric that you care about most, and then when this is satisfied, you begin to optimize for both the most prioritized metrics and the second prioritized metrics, and so on and so forth.
Yeah, I think so. There's a field called multi-objective optimization, right, which does basically try to optimize all objectives together. You can either do that or you can do phase-wise optimization. Yeah, I think that's a great idea, and yeah, I think we should work on that.
Of course.
Yeah.
Do you think it's important to have like human interpretable code as one of those objectives, or is that not?
No, I think that's a great point. And the short code actually goes directly against that. Right. It actually goes directly against. Yeah. I think that's a great point, but for that we need human annotations because that is a very subjective thing in itself. You might find some code more interpretable than I do. I don't like Pythonic code. I think the code should be robust enough. Very detailed so that I can understand it. But yeah, it's a very subjective thing.
But experts as well in a lot of cases.
Yeah.
So could you infer that from human behavior using something?
Yes, so actually I would like to recommend there's a great paper, not related to this work, but there's a great paper called Tom Sui. It's a theory of mind software engineering agents, which tries to do that. They try to have like another model which is learning the theory of mind of the user itself and then changing its behavior, changing the software engineering agent behavior. So I think that's a great point as well, and you can also do that. Yeah. Thank you.